Hi guys, today we'll continue confidence interval topic again. So we will finish actually how to construct confidence interval today. So I actually want to talk about delta method. So how we can find a function of a random variable whose variance is independent from parameters. Okay, so this is actually how Box-Cox transformation works also somehow. So basically, this is an approximation method again. We are using Taylor series expansion for any function of a variable actually. So when we have a linear or nonlinear function of one variable, then it can be always approximated by some function using Taylor series expansion. So the basic idea is that one. And using this approach, and using the again central limit theorem, combining this with the central limit theorem, and for large n, we can say that our sample mean always approximately normally distributed with some mean and variance. Then we can consider the transformation of x bar, any function of x bar whose variance is independent of parameters. So let's see that. It's not that easy to understand actually, but I want you to get some idea about how we can do that. And in the exam, I will not ask any questions related to this. Okay, so basically the main part is constructing diffusal quantities using location scale family type and finding diffusal quantities using distribution function. And we will see construction of confidence interval, exact confidence intervals using general method that we will see today. And also we have approximate confidence intervals using central limit theorem and the asymptotic distribution of MLE. So these are the things that you will be responsible actually related to the confidence intervals part. Okay, so let's see how we can use delta method to construct approximate confidence intervals. I remember in binomial case, and also for Poisson case, also for many discrete distributions, variance is a function of the mean actually. So in that case, that variance part creates problem actually how to get rid of it. So we have some solutions, but this is another solution. The transformation. Okay, so here a basic idea of this method is this, delta method is this. So we have a random variable y, let's say its expectation is mu, and its variance is a function of mu. Okay, this can be applied for a time series actually, or heterogeneous variance part. So if the variance is not constant, basically we can apply this method to stabilize the variance. So this is also known as variance stabilizing transformations. So here our aim is find a function of y. Okay, so this is a function of y, so it's a random variable also, whose variance is not a function of mu. Okay, so the basic idea is this one. So we know the random variable y, we know its distribution. Okay, but since in the construction of a confidence interval part, this part, variance of y, if it is a function of a parameter mu expectation, then it creates a problem. Then how can we solve it? This solution, delta method solution, requires this one. So we need to transform our random variable, okay, so that its variance is independent of mu. So using this transformation, basically we try to find an interval a function of a random variable, and from that we are going to create an interval for our actual parameter that we want to estimate actually. Okay. So we are using delta method to be able to solve this problem. Okay, so we are interested in uy. So this uy can be any function. Okay, any function, linear, non-linear. Okay, any function uy can be approximated by Taylor series expansion. So we know that from math. Approximated by the Taylor series expansion about our parameter, let's say mu here. Okay, it can be theta also. Okay, so how can we do that? Okay, so you know Taylor series expansion goes till infinity. It uses the derivative of the function itself. So, so when we want to use this in the ultimate, we are just using the first two components of the Taylor series expansion, assuming that others close to very zero, other parts close to zero. So we approximate this function by function u function where we replace y by mu. Okay, the first component. The second one, the difference between the variable and the parameter itself, and the change of those, so the derivative of the function, then replace y by mu. Okay, so let's say we will just use this part. It goes, you know, you have to use this the squares, cubes, and fourths, but we will use this in the delta method. So let's say this approximated function is vy. Okay, so we are approximating uy by vy. Here we have one assumption that this derivative exists and non-zero. Otherwise, we cannot use it. Okay, so here, then we need to find this vy, okay, so that its variance is independent from its parameter. So let's try to find expectation of this function, okay. Okay, so next expectation of uy then can be approximated by expectation of vy, okay, which is expectation of u mu plus v minus mu and the derivative function. Okay, so then we have u mu, okay, the other part becomes 0 because expected y is mu, then this one. So we can say that this equals to u mu. Okay, so it's an unbiased estimator of u mu vy. Then try to find variance. Okay, so approximate uy by this, so variance of vy. Okay, so variance of u mu plus y minus mu u prime mu. Okay, so the first part is constant u mu, so it is 0. Plus variance of y minus mu, so it becomes variance of y basically. So this part is constant, so they take the square. So this is same as the variance of y. So basically this can be approximated by u prime mu squared and variance of y. Okay, so using these, then we need to find a function. Okay, so we need to get rid of this mu function, and in variance y, the variance of y, actually this is a function of mu. Then we need to create a function. So this part is a function of mu. So based on the form of the variance, okay, then we need to find a derivative function first, okay? Then this derivative, square derivative function will eliminate the mu term in the variance of y. Then, after deciding that derivative term, the square derivative term, okay, then using the reverse, if we know the derivative, so we can go back to the original by integrating it. So we try to find the original u function based on this one, okay? So let's see an example. Maybe with an example we can understand it better. Okay. Yeah, okay. First of all, let me give this. For example, for large n, so this is true for any distribution basically, sample mean approximately by center limit theorem normally distributed with mean mu and variance sigma square over n, okay? So let's say we want to get rid of the sigma square term. Actually, usually the problem is when the mu and sigma are functions of each other's case, but let's see how we can apply this term. So basically, we need to find a ux bar function. So this is also approximately normal. Because when we approximate it by Vy, so it will be linear function of x bar, and we know that any linear function of a normal distributed random variable is also normal. So using that, this can be approximated, and we will get mean as this one, and variance as the square of the derivative, and variance of y, which is sigma square over n. Okay. And here, then, okay, so basically we need to get rid of the sigma if our aim is to be able to get the sigma square. So if sigma square is a function of y here, okay, then using this, then we have to create this part, okay? So let's say this is a function of mu, okay? And then we need to create this as some constant over sigma square, okay, as a function of mu, basically, okay? So the square derivative will be this one. So this means that regular just u derivative will be in square root c over sigma square, okay? So if we know that our derivative is this one, then integrating this helps us to get original u function, okay? U mu function or uy function. Okay, so the basic idea is this one. So after that, basically, after deciding our u, then we can use this, for example, in this case, using the standardization here, u prime mu whole square, then there will be no parameter in the standard error part actually. So in the denominator, there will be no unknown parameter after the derivative. So this will be limiting distribution will be standard normal. So using that, we can generate an interval form u mu, and then we can go back to our mu, the confidence interval for mu, if we have a monotone increasing or monotone decreasing function of u functions. Usually we try to create them like that. Okay, so main problem is in the discrete cases. So here, for example, Poisson. So Poisson is a problematic part because we know that both mu, mean and the variance are the same, mu. So if we want to use approximate, find the approximate confidence interval for Poisson parameter mu, then there will be mu term both in the mean and for the variance. Okay, so and this will create a problem because so let me write it actually. So let's say we have a Poisson distributed random variable with parameter mu, and here we know that expected x is mu and variance of x also mu. Okay, and then when we approximate x bar by central limit theorem, So we know that it is normal with mean mu and variance mu over n. Okay, so when we try to create an interval for mu, basically, when we standardize it, x bar minus mu over in square root, we have mu over n. So this will be standard normal. So using this, basically, so we can say that this quantity, probability minus the f over 2. Okay, so x bar minus mu in square root. So we have this, the f over 2. Let's say this equals to 1 minus alpha. But this, in the denominator, since we have mu term, so we have to get rid of that one. So we can replace it by mu hat. This is one approach. But we can use also a delta method. Instead of finding an interval for mu, we create a function. We try to find a function of x bar whose variance is independent of mu. So delta method helps us to get that. So find a function of x bar, let's say ux bar, okay, whose variance is free from mu. Okay, so let's focus on the variance part. So we know that variance of this transformed function approximated by this u prime mu whole square, and then the variance of x bar. Okay, so we want this independent of mu. Okay, how can we do that? So then when we look at the form here, so we have mu over n. So if we choose our derivative function as something over mu or in square root of mu, when we take this square, so these mu terms will cancel out. Okay, so then choose u prime mu whole square as some constant over mu. Okay, then this mu and this mu, so these two mu terms will cancel each other. Okay, so let's try to find the original u function. So it will be in square root some constant over mu. Okay, then if we know that derivative of function is this one, then how can we find the original function? So when we integrate it, this function d mu, basically we can find the original u function. Okay, so let's write this d mu. Okay, then we will have some constant. This part is not important, basically. So we have square root of mu, square root of mu. Okay, then we can say that our mu function can be written as some constant a times square root of mu. So if we apply, so this is a function of x bar actually, if we apply without loss of generality, if we choose this as square root of x bar without loss of generality, a equals to 1, okay, then the variance of ux bar will be independent from mu. Okay, so using this transformation and choosing our function like that, then we can create a function. So when let's look at it actually. So the variance of ux bar now will be, okay, so we will have 1 over 2 square root of mu whole square mu over n. As you can see now, our variance will be like that. Okay, so when we consider the approximate distribution of our ux bar, which is square root of x bar right now, then approximately normally distributed with square root mu as the mean and the variance as 1/4n. Then we can easily generate an interval for square root of mu. Okay. Okay, and 1/square root of 4n. So this has standard normal distribution. Okay, then we can say that after creating an interval minus that I/2, and actually we can write this part as a nicer form like this, and this should be also like that, and that I/2, this probability equals to 1 minus alpha. Okay, and then keeping mu alone, we get square root of x bar minus z I/2 over 2 square root of n and square root of mu. Okay, so square root of x bar plus z I/2 over 2 square root of n. Okay, 1 minus alpha. Okay, so taking basically the square of both sides, so we will get mu less than or equal to square root x bar minus z I/2 2 square root of n square 1 minus alpha. So this will be our confidence interval. Okay, and then so we can write 101 minus alpha percent approximate confidence interval for mu as mu less than or equal to in square root of x bar minus z I/2 2 square root of n whole square. Okay. Okay. So let's go to the new section, general methods. Okay. So I think this is the third one after the approximate confidence intervals. So a general method for obtaining confidence intervals. We will not talk about confidence regions actually in this level. So we can create also confidence regions, but we will focus on only confidence intervals. Okay, so previously we saw this is an exact confidence interval generation method basically. So we already saw how to generate confidence intervals using pivotal quantity approach. We have two approaches actually there. One scale location scale type families. The other one is the distribution function method. But sometimes, let's say we don't have a location scale family and we don't have a closed form CDF, so we cannot use that approach actually to create an interval. So in that case, so how can we estimate our parameters using an interval for that? So basically, if a pivotal quantity is not available, then it is still possible to determine a region So we will focus on the interval only for theta, but you can also generate a region using this method. Okay, so how can we do that? Okay, so this based on, again, one good point estimate of parameters, but it's not necessarily the minimum variance unbiased estimated, but it should have a good properties, like it can be a sufficient statistic or an MLE. Usually we prefer sufficient statistics here, but you can also use the MLEs. Okay. So here, let's say, again, we have a random sample of size n, and we have a joint PDF of these. And let's say we have 1s, actually this is a function of some random variables, whose distribution is a function of s and theta. Okay, it's a function of a parameter. So here we preferably choose s as a sufficient statistic. S will be a sufficient statistic for theta, or possibly some reasonable estimator. For the reasonable estimator, like Emily, as an Emily, but not required. Okay, so I focused on the sufficient statistics actually in my notes. So here, the approach is this one. So we have a statistic, let's say sufficient statistic S, and we know its distribution. Then using the sufficient statistic and its distribution, basically, we can create an interval using the distribution of the sufficient statistic we have, because that in that distribution we have a parameter actually. So we know that sufficient statistics distribution has to be a function of a parameter. So using this fact, actually, we can create an interval for theta. Okay, so basic idea is this one. So we have to find a sufficient statistic and then find its distribution, and then in some probability, basically, then with some certain probability, we can find a region for our sufficient statistic first. Okay, like in the pivotal quantity case, and then using the same approach, we create an interval for theta. Okay. Okay. Let me write it down. So each possible values, each possible value of theta. Okay, assume that we can find values h1 theta and h2 theta. So these are the upper and lower bound for the sufficient statistic, such that in probability, okay, so our sufficient statistic is between h1 theta and h2 theta. Okay, equals that probability alpha. Okay, so you after finding the h1 theta and h2 theta using the distribution of S, try to write this function, this interval for theta. Okay, if our h1 theta and h2 theta functions are monotone increasing or monotone decreasing functions of theta, then the resulting confidence region will be a confidence interval. So we will focus on this type of cases in this course. Okay, so h1 and h2 theta will be monotone increasing or monotone decreasing functions of the theta. Okay, so if we observe capital S, so if you observe, so we have a lowercase s. So this is a number right now getting from the sample, calculated from the sample. Then the set of values theta in the parameter space that satisfy, so this is outside of the interval, so we will use lowercase letters here, okay, form 100 1 minus alpha % confidence region for theta. Okay, so we said confidence region, but mostly H1 theta. So and H2 theta. If one increasing, the other one also increasing. So I never saw a case when H1 theta increasing, H2 theta decreasing case. So if one is increasing, the other one is also always increasing. So let's say these are increasing or decreasing, but both of them have the same pattern, function of theta. Then the resulting confidence region will be an interval. Okay, so we will focus on these cases. Okay, so let's see the theorem. Okay, so let's, again, this capital S be a statistic, mostly a sufficient statistic. Okay, so statistic of continuous random variable with CDF. So using CDFs are easier actually to define the H1 and H2 functions. So CDF, and suppose that H1 theta and H2 theta are functions that satisfy. Okay, so G function, when we replace H1 function here, it will be alpha 1, the lower tail probability, and when we replace S by the upper bound for S, so we will get 1 minus alpha 2. So this is the till the upper bound probability for each theta in the parameter space here, where we assume that alpha 1 is between 0 and 1, alpha 2 is between 0 and 1, and basically we assume that alpha 1 and alpha 2 equals alpha. Okay, then let's assume that we observe the S value from the sample, so we get the estimate. So B and observed value of S. Okay, so there's a capital S. So first, if assume that both H1 theta and H2 theta are increasing functions of theta. Okay, then how can we create an interval? Okay, then so we focus on the one-sided intervals first. So one-sided lower 100 1 minus alpha 2 percent confidence limit. Okay, confidence limit theta L is the solution of H2 theta L. So we are using upper bound for S to get the lower bound for theta. Okay, so we equate. We found the H2 value first, H2 theta value, then equate H2 theta value to S, and replace this theta by theta L. Okay, so theta L will be the lower bound. Okay, so similarly, so I will show you with a picture actually, so you can understand it better how this happens. So one-sided upper, then 100, 1 minus alpha 1% confidence limit. Theta U is the solution of H1 theta U then equals S. Okay, so we are using the lower bound for the sufficient statistic and equate it to S value, and then replace theta by theta U and solve this function for theta U. That theta U will be your upper bound for theta. And how can we find the two-sided interval then? So if alpha equals alpha 1 plus alpha 2 case, and assuming that alpha is between 0 and 1, then the same methods basically. So from H2 we get theta L, from H1 we get theta U. Okay, so this theta L and theta U is 100, 1 minus alpha percent confidence interval for theta. Okay, so then how this happens actually, so let's see. So this is the end of the theorem. So let's say we have f of x theta, and right now we assume that we have a single unknown parameter, so we will only focus on this case here for the general method. Single unknown parameter. Okay, so let's say we have S, which is a function of sampled items. So let's say, let me write capital S values, X values here. So let's say this is an estimator of theta. Okay, so first of all, we need to find a distribution of S. Okay, so this is S, this is, let's say, G of S, theta, and let's say we have this type of shape. Okay, and then we need to find, so for S, upper and lower bound. Okay, so this will be H1 theta, H1, saying H1 and writing H2. Okay, this one. And we assume that this tail probability is alpha 1, this tail probability is alpha 2, and in the middle we have 1 minus alpha probability. So basically we are using the same logic that we use in the pivotal quantity method. Okay, so we need to find the probability that our sufficient statistic here is between H1 theta and H2 theta. Okay, this probability is 1 minus alpha, and from here, after defining the H1 and H2 functions, first we need to find those using the distribution of S. Then we need to find an interval for theta. Okay, and let's say this is a V1 function. Okay, so x1 to xn, let's say this is also the probability, and V2 function. Okay, so we need to find H1 functions and using those convert this interval to a theta. Okay, then after this, basically we will skip this probability parts, immediately find the V1 and V2 functions. Okay, so confidence interval for theta, so we don't have to do a calculation in the probability, easily find the values. So let's see how to do that. Okay, so this will be the numeric values for the upper bound and upper and lower bounds. Okay, so let's try to draw the picture to see how this happens actually. So let's say, okay, so this is our parameter theta, this is our sufficient statistic. Okay, so let's say we have two functions. Okay, so let's say we have this h1 theta function and let's say h2 theta function. We assume that s is between h1 theta and h2 theta functions. Okay, h1 is less than h2 function. Okay. Okay, so let's say for a specific value of theta. Okay. Okay. So let's say our theta is this value. Okay. We want to find an interval for this theta value, let's say. Okay. Then in this h1 and h2 functions, basically using okay, so using the values here. Okay, so let's say our let's try to find a good place then. Okay, so let's say our h1 value is somewhere here and h2 is somewhere here. Okay, so we know that our s is somewhere is between. Okay, so the observed value. Okay, so we want to find a place where this s, okay, so these are the function values where this h1 and h2 function values are set, but we need to focus on the parts that we observed on this h2 and h2 functions where theta is observed. So so let's draw a line here, okay, and then in h2 basically, okay, this point is fixed, and then on the theta function, because we need to find an interval for theta, so here we obtain our v2 functions from h2, okay, sorry, v1 function, the lower bound, sorry, okay, and then on this, okay, so on h1 function, we obtain the upper bound for v2. Okay, so basically we want to find this v1 and v2 functions where actually this s is, you know, on this line. So what is the value of h2 theta? So when we obtain s, okay, so we obtain v1 here, and it will be the lower bound for theta. So using the upper bound for s, basically, we are obtaining a lower bound for theta. And similarly, okay, so where we are obtaining on h1 theta function when we have s, okay, so here on the theta axis, we obtain v2 upper bound. So from the lower bound for s, we obtain an upper bound for theta, okay? So we assume that in this case, these are strictly increasing functions of theta, okay? So we don't have the case where one increasing, the other one decreasing case. Both are increasing or both are decreasing functions of theta. So this will give us the confidence interval for theta. Okay, so we start with an interval h1 and h theta. Okay, and on the specific theta value, basically. Okay, so we obtain these first. Okay, so specifically for theta, we obtain these values. Okay. Then where on S, actually h1 theta and h2 theta has a map on the theta axis. Okay, so I'll try to find that. So, and then we can immediately write this as our interval, whatever those are. So this will be our confidence interval. Okay. So if you have the how to say the PDF basically, what we will do, so from minus infinity to h1 theta, get the PDF of S, the sufficient statistic here, equate this to alpha, because from here up till this point, h1 theta, the probability that we have is alpha 1, until h2 we have a probability 1 minus alpha 2. So this are the, so from here we will solve this for h1 theta, and similarly do this from lower bound of S to this ds theta ds, equate this to 1 minus alpha 2, and so for h2 theta. Okay, and then check both these, check whether increasing or decreasing function of theta. Okay, so if they are increasing functions, if h1 theta, h2 theta are increasing functions of theta, then equate S. Okay, so using the upper bound for h2, replace S by v1. Okay, replace theta by v1, sorry, and get the lower bound and equate S to h1 v2. Again, replace theta by v2, obtain v2. Okay, so it will be a function of S. So these are the upper and lower bound for the confidence intervals. Immediately you can write them. So basically find h1 theta, okay, and then replace theta by v2. Okay, so h1 v2 equals S. So this is basically known from sample lowercase, and then get v2. And from get the h2 theta, replace theta by v1, get h2 v1, equate this to S, and get h1. So then confidence interval for theta will be v1 theta v2. Okay, so what about if they are decreasing functions? So if h1 theta and h2 theta are both decreasing functions of theta, then basically just reverse the values of v1 and v2. So we will get S equals to h1 v1. So lower bound for theta can be obtained by the lower bound for S. Okay, get v1, and S equals h2 v2, get the upper bound. Okay, so from upper bound you get upper bound, lower bound you get lower bound. Okay, so let's try to draw its shape. So how can we get it? So let's say again, this part is theta, this part is S, and let's say we have two functions like that. So this is h2 theta, this is h1 theta. So these are decreasing functions of theta basically. So let's say we have S value. Okay, so we assume that our S is between h2 theta and h1 theta for specific value of theta. Okay, actually these will be like that. Then our main aim is actually finding. Okay, so let me try to get a better picture. Okay. Okay, so let me draw them again. Okay, so let's say then this part is our H2 function. Okay, so let's say we have S in the middle. Okay, so where in S our H2, H1 function obtained in theta axis, and then again for H1 what we get. So basically here when our S is hit to H1 theta function, we get the lower bound for theta. When RS hits the H2 function, it gets the upper bound. Okay, so here from here we can say that basically from lower bound of S we can get the lower bound for theta. From upper bound of S we get the upper bound for theta. So this part, these two region values gives us the confidence interval for theta. Okay. Okay, so let's okay, so for the one-sided cases, so it might be a bit confusing actually to get one-sided intervals. Okay, so when we have one-sided cases, so that here probability that S greater than of H1 theta. So when we start from here, what we will end up. So for an increasing function, if our H function is an increasing function or decreasing function. Okay, so what we will get, so probability that theta V2, okay, 1 minus alpha. So from lower bound of S, we get the upper bound for theta. And if it is a decreasing function, the reverse, basically, we get the lower bound, okay? And if we start from the upper bound for theta, okay, so basically for a decreasing function, we get the lower bound for theta and upper bound for I said upper bound, but right this way, upper bound for theta for a decreasing function. Okay, so you can use these actually immediately. Okay, again, let's focus on some examples. Okay, so our simplest example is exponential case. So when I want to explain the stuff, I usually use these kind of simple PDFs. Okay, so let's say we have a random sample of size n from exponential distribution. Okay, so so let's say x bar is our MLE, minimum values unbiased estimator of theta. It's also a sufficient statistic here. So here actually summation xi is a sufficient statistic, but you can also use this. Okay, so it is also the minimum values unbiased estimator of theta. So it's a good estimator to start with. And here actually we know that when we have an exponential distributed random variables, distribution of x bar is related with gamma. Okay, and then gamma is a special case of chi-square distribution, or the chi-square distribution is a special case of gamma distribution who has a statistical table. So if we try to create intervals like for this kind of statistical random variable who has a statistical tables that has a statistical table, then we prefer that one actually. So we know that 2x bar 2 and x bar over theta distributed as chi-square with 2n degrees of freedom. So we prefer, instead of using exponential gammas, we prefer to use this one. And let's say we want to find, so construct 100 1 minus alpha % confidence interval for theta using the general method. Okay. Okay, so let's say here if we want to find equal tail probabilities, let's say don't work with alpha 1 and alpha 2, assume that we want to get an equal tail probabilities. Okay, so first of all, okay, so probability that our statistic that we want to use is this one, right? And then we want to find lower bound and upper bound using the distribution of x bar, okay? And then after that, basically, so we can write this 2n x bar over theta is chi-square distributed, so 2n h1 theta over theta and 2n h2 theta over theta 1 minus alpha. Okay, so we know that this has a chi-square distribution. Then we can find the values of h1 theta and h2 theta easily. How can we do that? Okay, so we can write this probability as probability that, so we have a chi-square distributed random variable. This should be less than r h2 theta over theta minus probability that our chi-square distributed 2nx bar over theta, actually this part, is 2n h1 theta over theta. This equals to 1 minus alpha. Okay, so what are the probabilities of these? Basically, we know that because we know the alpha values. Okay, so let's draw the picture. So we have a chi-square distributed random variable, which is 2n x bar over theta. Let's say this is the distribution of that PDF. So we want to find upper and lower bounds here in the chi-square, and we want that these tail probabilities are alpha over 2. So now we know the distribution, so now we can easily write that we have chi-square 2n, then upper tail probability is alpha over 2, so chi-square 2n 1 minus alpha over 2. So this, till this part, we have alpha over 2 probability. So this this part is alpha over 2. Okay, and then now this part is till the upper bound. We have this part is 1 minus alpha over 2. Okay. Okay, then after finding the probabilities, then this quantity will be our chi-square value, and this quantity will be this quantity. Okay. Then our 2n h2 theta over theta will be chi-square 2n alpha over 2. Then we can write here alpha 2 8 as theta times chi-square 2n alpha over 2 over 2n, which is an increasing function of theta. Okay, and then similarly 2n h1 theta over theta will be chi-square 2n 1 minus alpha over 2. So from here we can get the value as theta chi-square 2n 1 minus alpha over 2 over 2n. This is also an increasing function of theta. See, both of them increasing. It should be like that. After that, actually, so we know that from the theorem, if h1, h2 theta are increasing functions of theta, so we choose our statistics as x bar, then, okay, so lowercase x bar, the sample values. So from the upper bound, we obtain the lower bound. Okay, so on the h2 function, when we saw theta 1, and then replace this theta by v1. So v1 times chi-square 2n alpha over 2 divide by 2n, and from here we can get v1 as 2n x bar over chi-square 2n f over 2. Okay, so this will be the lower bound. Okay, and then for the upper bound, x bar equals h1 v2 equals, again in the h1 function, replace theta by v2 chi-square 2n 1 minus alpha 2 over 2n, and from here v2 obtained as 2n x bar over chi-square 2n 1 minus alpha over 2. Okay, then our interval will be immediately written, can be written as for theta. Okay, so our v1 is 2n x bar over chi-square 2n alpha over 2 and 2n x bar chi-square 2n 1 minus alpha over 2. Actually, as you notice, this is exactly the same interval that we obtain by distribution function methods. So for exponential distribution, we use scale parameter approach, obtain a pivotal quantity, and using its distribution, we get an exact interval. And we also use distribution function method to obtain pivotal quantities and get an interval. And for using general method, we get the interval. And all these three are the same, gives us the same intervals. But this is not necessarily the same for all distributions, basically. Okay, so let's solve more questions, actually. Then you can understand them better, but I need to I need to give a little break. I will continue. There's my Zoom. Okay, I will just so let's continue. Sorry about that. Okay, let's solve more questions, actually. So with more questions, you can understand these topics better. Okay, so let's find an interval using general methods for the uniform distribution. So let's say x distributed as uniform 0 theta. So using the scale parameter approach, basically we can we found an interval. Okay, random sample. Okay, so our question is here: find a confidence interval for theta using the general method. Okay. If you remember here, both MLE and also the sufficient statistic is this nth order statistic here. Okay, so S equals to xn nth order stat. So we need to work with the distribution of order statistic here. Okay, so we can use immediately the CDF. So CDF of x here, you will get x over theta. Okay, and then the CDF of S, which is the CDF of x and basically the nth power of this. Okay, so we can get an equality here, doesn't matter. For immediate, it's important actually to write an equality sign. Okay, so this is our CDF. Okay, so using the method, basically, what's our aim? We need to find probability that where our sufficient statistic, which is nth order statistic here, we need to find upper and lower bound for that. H1 theta and H2 theta. Okay, so this equals to 1 minus alpha. And from here, we can write this as, you know, from the basic probability, the CDF of H2 theta minus the CDF of H1 theta equals 1 minus alpha. Assuming that we have equal tail probabilities, oops, this probability, okay, so this is the from lower bound till the upper bound of S, which is 1 minus alpha over 2 probability, and this probability is from the lower bound to H1, okay, so it is alpha over 2 lower tail probability. Okay, so you can imagine the pictures. Okay, so get these probabilities. So we know the probabilities. So we need to find H1 and H2 functions. So basically we know the form of H is a G function. So in that G function, just replace this x's by H1 and H2. Okay, so H2 theta equals to then H2 theta over theta to the n, and this equals to 1 minus alpha over 2. Okay, so let's first find H2 theta. Okay, then our H2 theta will be theta times 1 minus alpha over 2 and root. Okay, similarly, H1 theta equals H1 theta over theta to the n, equate this to alpha over 2. Okay, then from here, H1 theta equals theta times alpha over 2 n. So now focus on the forms of H1 and H2 theta, whether they are increasing or decreasing functions of theta. So here, as you can see, these are functions of theta. So both functions are increasing functions of theta. Okay, so this means that from lower bound of S, we will get upper bound for theta. Okay, then this means that when we equate xn, okay, so when we use the upper bound for xn, we will get lower bound. Okay, and similarly, from the lower bound for xn, we will get the upper bound for theta. Okay, so here we replace theta by v1. Okay, then we have 1 minus alpha over 2 and power. Here v2 alpha over 2 to n power. Then our lower bound v1 will be nth order statistic over 1 minus alpha over 2 to n, and v2 equals xn and order statistic alpha over 2 to n. So from here we can say that 1 minus alpha percent confidence interval for theta will be nth order statistic and alpha over 2 to n. Okay. Okay. Let me solve one more question. Actually, I will solve a question that we use in the problem time, in the lecture hour that I use. Actually, I don't have the solution right now with me. I hope we will not have any problem. So let's say we have a random sample from a PDF that we used before, 2x over theta squared, okay? So it was like that, as I remember correctly. Okay, so here again, the nth order statistic is a sufficient statistic. So S is xn here. Okay, also the MLE. So let's find the distribution function. Okay, first, so from 0 to x. 2x over theta squared dx. So we have x squared theta squared x theta. So then gs, which is gxn, will be just the nth power of the, CDF. Okay, now our aim. is this one. So probability that our nth order statistic, sufficient statistic here, we want to find h1 theta and h2 theta. Okay, this equals to 1 minus alpha. Okay, so then this equals to then h2 theta CDF minus the h1 theta CDF is equals to 1 minus alpha. Okay, so we are using the same logic. Let me now draw the picture. So let's say this is the PDF. So let's say we have this shape, okay? So we want to find these 2 points, which on the lower one was h1. So this is not theta, sorry. This should be xn. h2 theta, and let's say again, let's use equal tail probabilities. We can use alpha 1 and alpha 2 also. Let's use alpha over 2, alpha over 2 here. Okay, so till h2. Okay, so this is h2. So till h2, what is the probability that we have? 1 minus alpha over 2. Okay, so this probability is 1 minus alpha over 2. Then till h1, so this point, what is the probability? Alpha over 2. So this probability will be alpha over 2. Okay, then we know our CDF. Okay, so this is our CDF. Then when we see xn, we will replace it by h2 theta. And equate it to 1 minus alpha over 2. Okay, so we have then GH2 theta equals to xn theta to 2n. Let's write it this way, 1 minus alpha over 2. Okay, then our, sorry, I need to replace this by h2 theta. I copied it. h2 theta, obtain h2 theta. This is again the increasing function. Okay, so theta 1 minus alpha 2, 2n. And similarly, gh1 theta. Okay, so h1 theta, 2n alpha over 2. And from here, we get h1 theta as theta, alpha over 2, 2n. So again, when we look at the form here, these are both, again, increasing functions. I will find a function which is decreasing the lecture for the lecture time, decreasing function of theta. Okay, then this means that when I equate our sufficient statistics to h2, I will get the lower bound for theta. Okay, so v1, 1 minus alpha over 2 to 2n. Maybe when we use, if the first order statistic, let's see. Okay, so I will try to find an example for the decreasing case. Okay, h1, v2. So v2 equals v2 times alpha over 2, 2n. So from here, we get v1 as nth order statistics over 1 minus alpha over 2 to 2n, and v2 equal nth order statistics over alpha over 2 to 2n. Okay, so this means that 100, 1 minus alpha % confidence interval for theta is xn 1 minus alpha over 2 2n theta xn. Basically, we don't work with the probabilities here, so immediately you can write the intervals. Okay, so this will be the interval that we will get. Okay. Okay. So basically, for discrete cases, it's not that easy to find the exact intervals, especially if we want to get exactly one specific confidence level. Okay. So let me. So one question related to that. Basically, if we say 95% or 90% confidence interval, it's not possible to get exactly that probability for discrete case, because we don't have, we have only limited number of values, for example 3 or 5, but not 3.5, for example. Because of that, it's not easy to get exact probabilities. We will have the same problem in the hypothesis testing, the significance level case. So we will see the randomized test concept here. So let's say we have a Bernoulli distributed random variable where theta is between 0, 1 and x only takes 0, 1, and we know that summation xi is the sufficient statistic and binomial distributed. Okay. And we know that y over n, or x bar, is the MLE of theta, also minimum variance unbiased estimator of theta. So let's say we have a sample of size 20, and we observe that y equals to 4. Okay, this is our S, sufficient statistic. And we don't want to find approximate interval, we want to find an exact confidence interval for theta here. Okay, we already found the asymptotic distributions. Okay, so we want that, but alpha here, or 1 minus alpha term, is close to 0.95. So we know that we cannot get exactly 95%. Okay, so what we will do, okay, so we will use two equal probabilities again, and we want that these are about, not exactly, okay, 0.025, and then we will find probability that our sufficient statistic is less than or equal to y, which is 4, we observe, okay, and then from here we get v2, okay, and then again with the same probability, about 0.025, we get y greater than or equal to 2, 4, and here we get the lower bound. Okay, so we can exactly write this part as 1 minus probability y less than or equal to 3, because we can use cumulative binomial tables in that case. Okay, so basically what we did here, we approximately get alpha over 2, get the sum, let's say t from 0 to h1 theta, okay, and choose t, theta to t, and 1 minus t to the n minus t, and from here, after finding the h1 theta, we get v2, and similarly, equals 0, h2, no, sorry, I write 1 minus, I forward to not 1 minus, I need to write it a different way, from n to t to t to h2 theta here, okay, so n choose t, theta, 1 minus t to the n minus t. Actually here, so we can write this part as S, which is H2V1, and here we can write this as H1V2, okay? And from here, we get a lower bound for theta. Okay, so let's use the cumulative binomial table using the cumulative or specifically n equals 20 and y equals 4, because we obtain all these. Okay, so we have cumulative binomial table. Okay, here we have specific theta values. Okay, so we go to the n equals to 20 case, and y equals to 1, 2, 3, 4, and it goes till 20 or 90. Okay, so we specifically want that our alpha over two values will be 0.025 approximately. Okay, so basically when y equals to 4, go to the cumulative probability here. So we get alpha 1 equals 0.051 actually, and in that case our theta value obtained as 0.49. Okay, and then for 3 we need to get 1 minus alpha, remember. Okay, so we obtain 0.9841. These are the closest values that we get actually. So here alpha 1 value, alpha 2 value is 0.0159. So in that case, our probability value is 0.05 for theta. Okay, so using these cumulative probability values, find approximately 0.025 values. So these are the closest values to 0.025. Okay, so let me write them. Okay, so this is the closest value that we get for 25, and this is the closest value that we get actually. Okay, so not that close, but from the table, these are the only possible values for y equals to 4 and y equals to 3 cases. Okay, so these values will give us an interval for theta. So when we choose alpha 1 as 0.051 and alpha 2 as 0.0159, then basically 1 minus alpha score will be 0.9331. So it's close to 0.95, but not exactly as you can see. Then we have 93.31% confidence interval for theta will be 0.05 and 0.49. So this is one example of how we can find an exact interval for binomial. For Poisson also you can use the same approach using the general method. Okay. Okay, so I have one more note here for the construction of the region for the joint estimation for normal distribution mu and sigma square, how to get a simultaneous confidence regions. But actually, I want to skip that part. Basically, we are using the Bosso theorem where x bar and s square are independent from each other when we want to find and confidence region for both mu and sigma square. So in that case, it's basically you have to be careful about the probabilities. If you want to get, let's say, 95% simultaneous confidence interval for both mu and sigma square at the same time. So we were talking about a region. So here, by using the Bosso theorem, distribution of x bar and s square, or the probabilities that we obtain for x bar and s square, will be independent from each other. So when we consider 95% confidence intervals for both x bar and s square approaches actually, so the multiplication will not give us 0.95. Multiplication give us 0.97, approximately 97%. So you need to work on the confidence levels for two approaches. Okay, so I will skip that part. It might be confusing for you. Okay, so basically we finished the construction of the interval case. I will add more. So we will solve extra questions in the class time. Okay, and next week we will start hypothesis testing part. Okay, I think my previous last year's recordings start from the hypothesis testing, so I will not record new ones. I will just let you to get my last year's recordings. But at that time, we didn't have actually Zoom, so I had to prepare the records by using my tablet and then recording onto that, and it was huge. So I need to separate my video recordings to 3 or 4 or 5 segments, like I did in the last semester. Okay, so they will be like that. Okay, so see you in the class time. So please, if you have any questions, so we can discuss it in the class. I don't know, I will prepare an H5P versions of these or not. Let's see. Okay, so see you. Take care. Bye, guys.